The learning objective of this video is to give the starting material, mechanism, and product for a base catalyzed Aldol reaction. So my initial starting material is going to be an ethanol, and the solvent needed for this reaction is a strong base, so I'll be using hydroxide. So to start off with this mechanism, we need to locate an alpha hydrogen. So this alpha hydrogen, which is in green, is connected to an alpha carbon, which is the carbon connected after a carbonyl. So to begin, the hydroxide is going to be attacking this hydrogen, and this is going to form a water molecule. And now the electrons between these two are going to go to this carbon and form a carbon anion. So the carbon ion, which forms right over here, has a resonance structure known as the NO-loate. So the carbon anion is going to be acting as a nucleophile because it is electron dense. So it's going to be attacking this carbon from this different ethanol because this carbon has a slightly positive charge because of the oxygen. So the carbon anion is going to attack this carbon, and then the electrons between the carbon and oxygen are going to move to the oxygen. So now we have this intermediate before we reach our final product. So this oxygen is going to have a negative charge because of the lone pairs it has. So this oxygen is going to attack the water molecule that we formed earlier, forming an alcohol right over here, and then we're going to be remaking our base. The aldol that was just formed for our mechanism can also have a different reaction. So this aldol can react with another hydroxide and form a double bond right over here. So in order for this to happen, we need to have another hydrogen in the alpha position present, which is right over here. So this hydroxide is going to attack the hydrogen, and then the electrons from this carbon and hydrogen bond is going to form a double bond over here. So now this carbon-oxygen double bond is going to become a single bond, and the electrons from here are going to be going to this oxygen. So now the oxygen has 3 lone pairs and the bond, which now makes it have a negative charge. Now one of the lone pairs is going to go right back to this carbon-oxygen bond, forming a double bond. Now the double bond that was formed is going to go to the adjacent position right over here. And in order for this to happen, this OH has to be kicked off. So the OH is going to get kicked off, and we're going to be left with this as our final product. Now I'll be going over some practice problems before I do some synthesis-based questions. So for this first initial question, I'm going to have ethanol and acetone present. As you can see, both ethanol and acetone have alpha hydrogens present, which are colored in green. So this means that both acetone and ethanol can act as nucleophiles because they can both be deprotonated. So we're going to have a combination of 4 products. So the reason we're going to have a combination of 4 products is because acetone can react with another acetone, ethanol can react with another ethanol, or you can have a combination between ethanol and acetone. So our first initial product is going to be the acetone reacting with the acetone. As you can see, this product has 6 carbons, which does make sense because an acetone has 3 carbons. So when you have an acetone reacting with acetone, they're both going to combine. So the bond is going to happen between the 2nd carbon and the 4th carbon, or the carbon from an acetone over here and from another carbon with another acetone. So then one of the acetone is going to remain with a ketone, and then the other acetone is going to have its ketone become an alcohol. So our second self product is going to be ethanol reacting with ethanol. As you can see, this product has 4 carbons in total, which does make sense because ethanol has 2 carbons, and when you react 2 ethanols together, you should have 4 carbons in total. So one ethanol is going to remain as an aldehyde, and then the second ethanol is going to have the aldehyde become an alcohol. So now the last 2 products are going to be a combination between ethanol and acetone. So either the acetone can be a nucleophile and attack the ethanol, or the ethanol can be a nucleophile and attack the acetone. So for our first case, we're going to have the acetone be the nucleophile. As you can see, this final product is going to have 5 carbons, which does make sense because the acetone has 3 carbons and the ethanol has 2 carbons. So in this case, we're going to have the acetone attacking the ethanol. So this means the ethanol is going to have the COH double bond become an alcohol. So then for our final product, which is going to be similar to our other final product, we're going to have the ethanol becoming the nucleophile and attacking acetone. So in this case, the ketone and the acetone is going to become an alcohol. And as you can see, the bond formed between the ethanol and the acetone happened between 2 and 3. In this reaction, we're going to be having ethanol reacting with benzaldehyde. So we notice that both of these molecules have an alpha carbon, but there's a problem with the benzaldehyde. This benzaldehyde does have an alpha carbon, but there's no alpha hydrogen present. As you can see, this carbon right over here is double bonded and it already has two things connecting towards it. So that means that the benzaldehyde has to be electrophile in this case. So that means that the ethanol is going to be the nucleophile in this case. So we're going to have to imagine that once the alpha hydrogen is removed, that the carbon right over here is going to connect to this carbon. And once that happens, this oxygen is going to become negatively charged and then eventually an alcohol, as you can see in our final product. So now I'm going to be doing a question that involves intermolecular forces. So as you can see, we're going to have this symmetrical molecule. Since this molecule is symmetrical, you're only really going to form one product. So what's going to happen, so the problem with this starting material is that we have two alpha hydrogens present. We're going to have one in green and then one in red. So that means one of these alpha hydrogens is going to be better than the other one. So if we're going to be doing a reaction that involves intermolecular forces, we have to see what type of product we're going to form. And if we're going to have one of these alpha hydrogens reacting and being deprotonated, we're going to form a carboanion. It's going to be reacting with this carbon right over here because this carbon is slightly positive. So we're going to be forming a cyclic ring. So we have to figure out which cyclic ring is going to be better or more stable. So let's imagine if we remove this hydrogen right over here, and now this carbon over here is negatively charged. So let's count the carbons and see how long this ring would be. So we have 1, 2, 3, 4. This isn't really good because a 4-carbon cyclic ring is not really that stable. So this means that we have to remove the red alpha hydrogen. So if we remove the red alpha hydrogen, imagine this was the carboanion. Let's count the carbons, right? So we're going to have 1, 2, 3, 4, 5, 6. So we're going to end up having a cyclic ring that's 6 carbons long, which is very stable. So let's start off with the mechanism, or showing off the mechanism. So we're going to have the starting material right over here. We're going to have the hydroxide attack this alpha hydrogen, the red one, because it's going to form the most stable cyclic ring. And now it's going to be forming a carboanion because of the electron transfer. So now this is where intermolecular forces play in. So we're going to have the carboanion attack this carbon right over here. And the reason it's attacking this carbon is because this carbon is slightly positive because of how it's connected to an oxygen. So now we're going to be forming a cyclic ring. I would recommend labeling your carbons so you know which carbons have what substituent. So now we're going to have this as our intermediate. So we notice that this intermediate is going to be a 6 cyclic ring carbon, which is very stable. So now we just have to reprotonate this oxygen right over here. We're going to be doing that by using the water molecule that we formed initially from this initial part of the mechanism, because the OH reacted with the hydrogen, forming a water molecule. So our final product is just going to be this cyclic ring, second carbon right over here, and now we're going to also have an alcohol, a methyl, and carbon 6. So now I'll be going over some retrosynthesis questions. So we're going to try to get this product, but we have to figure out what initial starting materials we have. So we have to think about what we learned today. So we know that we can form this type of double bond if we have an alcohol over here and an alpha hydrogen present. So if we start imagining there's an alcohol over here and hydrogen present, alpha hydrogen present over here, that means we have to use a hydroxide in order for this double bond to be formed. So now this is our precursor to our final material. So now we have to figure out how we created this. So we notice that we have an alcohol here and a ketone present. So this means that we had a nucleophilic attack where this carbon right over here lost the alpha hydrogen and attacked a carbon over here that was positively charged, because slightly positively charged, because it's connected to an oxygen. And the only way that can happen if we have these starting materials and our solvent be hydroxide. So I'm just going to show you guys the initial starting material and like the synthesis for it. So it does make sense that this is the initial starting material because this is attacking the other product or other reactant. So we're going to have this hydroxide remove an alpha carbon or alpha hydrogen from right over here because this alpha carbon has no hydrogens. So then this carbon is going to become a carboanion, and then it's going to attack this carbonyl, and then we're going to have this hydroxide present so that it can form a double bond. Now for this final synthesis question, we're gonna have this as our final product. So now we have to figure out what was the starting material. So we see that we have an aldehyde group right over here and an alcohol group right over here. So let's go to the aldehyde and label these carbons. So we're gonna label this carbon alpha, and then we're gonna label this carbon beta. So we know for an aldol reaction, we need to have an alpha hydrogen on an alpha carbon. So we do have a alpha carbon right over here. So if we imagine that it was deprotonated by a hydroxide, that it attacked this molecule right over here, so it could form an alcohol. So if we were to erase this bond over here, oops. So if we were to erase this bond right over here, we will have our starting material for the left side. So now we have to figure out the starting material for this on the right side. So if we notice that when we do these types of reactions, that we usually have a carbonyl group. So if we imagine that this alcohol formed a double bond right over here, and we remove this H right over here, we notice that we have acetone, which does make sense because this carbon had 4 things attached to it. So now we can clearly see that these two materials are starting materials. So now let's go over the synthesis of it. So we know that this carbonyl has to be the starting material because the alpha hydrogen is present in this alpha carbon right over here, similar to in the initial problem. So that means this alpha carbon is going to lose its alpha hydrogen and become negatively charged, becoming a carbonyl. So this carbonyl is going to attack this acetone, forming this as our final product. And then we have to notice a slight difference between this retrosynthesis question and the first retrosynthesis question is that this retrosynthesis question doesn't have a hydroxide present on the bottom, while this one does. So the reason we don't want a hydroxide present right over here is so that we don't form a double bond. Because if we had a hydroxide present right over here, we would lose this alcohol. Oops. So we would lose this alcohol right over here and form a double bond. But this isn't the product we're trying to form. We're trying to form this product. So just be careful that you don't add an extra hydroxide group or you're going to end up with a double bond.